it's easier to write it.
It's much easier to see because almost everything's a lot.
Yeah,
Python's easier than Java.
I think
Python's the easiest.
I've never, my first language was whatever
I just like the ability to say, well, you want to pass through there, thank you.
Sure.
You want to return 5? Okay. Somebody, you want to declare something and then change the size of it and then things and make more. Python doesn't. Doesn't matter.
My first language was Visual Basic, but after that it was Java. It was Python integrated into Java. Yeah, it was really fun though, because it sort of had everything broken up into its own little methods, and then it was like practice, and you could call those methods. It was the whole entire language was just calling methods. There's nothing else you can do other than calling methods, passing values in return.
For you, I was going to say I gave you anything there, except for an also. You just messing with me?
Yeah, I just see that. All the time I mess with all my students. Well, no, I wasn't sure if I should just grab it now or wait for it to come by the line. It's all right there.
His display ability to
Don't
count.
judge me if I can't do that.
No thanks. I see how that worked during the exam.
I actually ripped it off, I was like, this is weird. You gotta take them off.
Let me just stop there. This one came in.
You see it.
I think. I found it.
Thank you.
Sure.
It's over there now.
Thanks, sir. Turning these things in sometimes.
Do you know Marcin?
Do I know Marcin? Maybe.
Oh, he's a Polish guy. He's from Poland.
Maybe. I probably remember him if I saw him.
Okay, he's a friend of mine. He said hi.
Oh, okay. Now I feel bad. Okay, so we don't have to, but we're going to start into our next portion of the course where we do direct proof. And today we're going to focus on the easier types of direct proof, although I don't necessarily know if there's anything as easy as anything that has proof in it, but hopefully you guys will see that it's not too terrible initially. Okay, so I guess for the next month we're going to be studying methodologies of proof: direct proof, indirect proof, inductive proof. Okay, so yeah, proof. So sorry about that. I might have said this before, but in case I didn't, this portion of the course is going to be a little bit more difficult than the first portion. So sorry, it's just the way it rolls. Okay. And then the assignment number 4 is going to be due on Monday, and all that stuff's going to be the direct proof stuff that we're doing recently. Okay. And I do have your guys' examinations. I'll give them back at the end of the class, and then I think I posted the solutions. If I didn't, somebody yell at me. Okay, good. So I did good stuff. Okay. I don't know if that was helpful or not, because you might not have remembered what you wrote down. So I'll give those back to you guys at the end, and then if you guys have questions for me, make sure you ask, okay? In general, they were very good, so I didn't have any problem, I don't think, with anybody's, well, mostly anybody's. I'm just messing with you, Donnie. All right, so questions before we get started, guys? Okay. So what we're going to do today is we're just going to get an overview as to what direct proof is and try to do some of the direct proofs. But basically, direct proof is a method to prove universal statements that we can't utilize exhaustion for, okay? On the examination, I did have a question to where I asked you guys to prove something, and it was fairly easy because you could exhaust everything, all right? I want you guys to consider, don't write this down because I don't know if it'll be helpful or not, but sum of two evens is even, okay? So, think about this, guys. Somebody throw out two even numbers to me.
4 and 6.
4 and 6, okay, so 4 plus 6 is 10, which is even, right?
Yes.
Last time I checked, okay? Somebody else throw out two more even numbers.
6 and 4.
6 and 4. Somebody who's not a jackass throw out two more even numbers that are not the same as what we already
12
got.
and 16.
12 and 16, which is 28. Even. All right, two more. Now everyone's afraid. What is it?
2 and 8.
2 and 8. Okay. And you guys get the idea that it looks like that no matter what two integers that we add that are even, it's going to be even, right? Mm-hmm. Now, what's the problem with trying to prove this?
Currently, we know exhaustion.
Oh, yeah. Currently, the only methodology we know to prove a universal conditional statement is by exhaustion, right? And how many pairs of even integers could we come up with if we really wanted to?
Infinity.
Infinite, right, guys? So, we have an inkling it's true, right? The problem is, how do we prove it? And that's what we're going to be doing for the next portion of the course. How do we prove things that we think are true, okay, or we have a good idea that are true, but we don't necessarily know how to do it by exhaustion, okay? So, I just wanted to go through some basic definitions, and then I'm going to show you guys like some of the algebraic technique necessary. Then we're going to go through the direct proof stuff, okay? So, I know we already went through some of these things already, so. So we know what an even integer, right, guys, is if we see z even, okay, we know that that just means that we're looking at an even integer. And this is the definition that we want to be interested in, okay? If you see that n is equal to 2k, that means it's an even integer, right? Like for instance, guys, the number 10. 10 is equal to 2 times 5, right? So that means it has to be even, okay? The number 28. The number 28 is 14 times 2. That means it's even, okay? Every even integer contains a factor of 2. That's the definition of even, okay? No matter how you write it. The definition of odd is that it's equal to 2 times an integer plus 1, okay? So, somebody throw out a nice easy odd integer for me. 3, okay? So, 3 is equal to 2 times 1 plus 1, okay? It fits the form. Somebody else throw out a nice, easy, even, odd integer, excuse me.
7.
7, okay? 7 is equal to 3 times 2, or I'm sorry, 2 times 3, it doesn't really matter, plus 1. Every odd integer can be written in that format, okay? So that's the definition of odd. If you can't write an integer such that it's 2 times an integer plus 1, it's not odd, okay? So we're going to be seeing that's the definition. So guys, do we understand the definition of even and odd, okay? That's what we're going to have to utilize. And that's for every single even or odd integer, okay? Perfect square, okay? Perfect square can be written in the form of something equals k squared, okay? And that's really easy, right, guys? You've been doing that all your lives. Like, for example, if I had the number 81, that's a perfect square because it's 9 squared, right, guys? Okay? That's the definition of a perfect square, okay? If you can find some number that when you square it, it equals that number. Or in other words, the square root of that number, okay? All right, one of the most important definitions we're going to be using is this thing called integer closure, okay? When we talk about closure, okay, closure means that if you perform an operation, it's still in the set of that numbers, okay? So, let's say, for instance, if you added 2 integers, okay? Like, for instance, if I added something like 130 plus 75, okay? 130 plus 75 is 205, which is an integer, right, guys? So it looks like if I add 2 integers, The result is an integer, okay? The same could be true of subtraction, right? If I do 130 minus 75, that's going to be 55, which is an integer as well. If I multiply two integers, let's say I take 130 times, not 75, 2, because I'm lazy, that's 260, which is an integer, right guys? So addition, subtraction, and multiplication are all closed by integers, right? That's what we mean by closure. Well, why not division? Why is division not closed?
Oh, rational, it could be rationalization.
It could be a rational number. Could you guys give me an example of two integers when you divide them, it doesn't give us an integer? 4 and 3. Perfect, okay? 4 over 3 is not an integer. So closure is not extended to the set of integers over division, okay? So, does that make sense, guys? When we talk about closure, if you add, subtract, multiply, square two integers, okay, it's all closed under integers, okay? So, if I added two arbitrary integers, I know that I get an integer out of that. If I subtract two arbitrary integers, I get an integer, multiplication, okay? So, I just have some basic examples. It just says to show, it doesn't say to prove. Andre?
Is this just for integers?
There's
So
other sets as well.
Okay, so I mean, is this rule of closure, is that just set to integers?
Not necessarily.
Okay.
Like for
We're
instance,
just working with integers.
right, for right now we're only working with integers.
So you're saying it's the sum or the product of these two integers is equal to an integer.
That's correct.
So it has to stay the same type of number, is that
Correct.
what you're saying?
Basically like a data set, okay? Like when you define variables, okay? Like if you define like an int plus an int, you get an integer output, right?
Right.
If you define float plus float, you get a float output. However, if you do float plus int, you guys get what out of that?
Float, right?
It always truncates into
Oh, yeah.
Depends on the language.
Right, okay, never mind, okay, you're right. I was thinking because most of you guys either do C or C++, but yeah, it depends on the language. Yeah, with C, it'll go out to an integer, so it just truncates all the float stuff. But regardless, for right now, we're only dealing with integers, okay? It actually is true for rational numbers, okay? For those of you guys that have to suffer through linear algebra, you get to prove more of that stuff. But for right now, it's just integers. Okay, anyway. So let me show you guys like just a few examples of where we can show a specific number or even a specific structure to be even or odd, okay? So 37 is an odd integer. You guys know this, right? Because 37 is equal to 2 times what number plus 1? 2 times 18 plus 1, okay? It fits the form of an odd integer. So if I ask you guys to show me that 37 is odd, that's how you do it, okay? Does that make sense to everybody, guys? Not difficult. If I asked you to show me that 2x plus 4 is even, that has to be equal to twice some integer, right guys? But we don't know what x is, okay? So does anybody think they might know how to show that that's even for any value of x?
Take the common.
Okay,
Two
because there's a
common.
factor of 2 in there, right? So if you factor out a 2 as a greatest common factor, some nasty algebra here, what do we get? X plus 2 in there?
Yeah.
Okay, so that's by factoring. We don't know what the value of x is, right? But what do we know about the domain of x? It's an integer, right guys? What is 2? Integer.
Okay.
So we have an integer plus an integer, which
Closure.
means that we have an integer by closure, right guys? Didn't we just say that by closure, if you add two integers, you get an integer? So that's some different integer, right? Like maybe y, maybe p, maybe q, maybe theta, maybe zeta, whatever letter you want. Let's just call it 2n, where n is an element of the integers. Okay? If you want to define n as equal to x plus 2, you may, but you don't have to. Okay? I can see that by transitivity, x plus 2 is the same thing as n. Okay? As long as those are integers. Okay? So we're just going to justify these steps. We're going to say this is by factoring, and this is by closure. You don't have to put integer closure because I already know that 2 and x are defined as integers. Okay? And right there, what we've done is we've proved that for no matter, well, we haven't proved yet, but we've shown no matter what number of x you plug in there, it's got to be even because it fits the form of 2 times an integer. Okay? So does that make sense, guys? Any questions about how you guys might show that a structure might be even? Basically contains a factor of 2. Okay? Now, what about this animal? Okay, we have our 6y plus 8x plus 7, and I need to show that that is odd. In other words, 2 times an integer plus 1. All right, suggestions? Sean?
6y plus 8x plus 6 plus 1.
So usually, nice. So usually 7 is 6 plus 1. Now how come 7 is not 5 plus 2 or 4 plus 3? How come 6 plus 1?
Because we have to
You want a plus 1 so you can prove it.
We need a 1 out of that. Nice, okay. So let's rewrite this. 6y plus 8x plus 6 plus 1, okay? Nobody doubts that 7 is 6 plus 1, right? Oh boy, that would be bad, okay? We'd be SOL at this point in the course. That's just by computation, right? And then as you suggested, we can factor out a common factor of 2, not from everything, but from just those first 3 terms, right guys? So we would get twice the quantity of 3y plus 4x plus 3 quantity plus 1. Okay. That's just the GCF. Nobody in here doubts that, right? We all know algebra 1. Might not be common core algebra 1, but okay. And then finally, guys, what do we know about 3y plus 4x plus 3? It's an integer, right? It's 2 times some integer now, right guys? We don't care what the values of x and y are. We define x and y to be integers up here, okay? Just like a computer program. If you add a bunch of integers together, the output's going to be an integer, okay? So that's going to be 2n plus 1, where n is an element of the integers, okay? So we have to make sure that we're defining our new variable. Just like a computer program, anytime we introduce a new variable, we have to define that variable. Okay, well, let me rephrase that. If you want full credit for that, you want to define your variable. Okay? So, this is by closure, and we are done. Okay? Guys, when we get to doing the stuff with the integers, this is the algebra stuff that we have to do. And the algebra is no more than algebra 1 at this point, right guys? It'll get a little tougher as we go along, but so far it's pretty tame. Okay? So, does everybody understand the process that we're utilizing to show that numbers are even and odd? Okay? Go ahead, Ryan.
Are there more rules than just?
There are, and for right now we're just dealing with integers. Eventually we'll get to rational, divisibility, floor and ceiling, irrational.
So for integers, is it just these?
For right now, yes sir. Okay, and that's all the ones that we need to know for our class. Okay, go ahead.
Can you explain what we're doing from the last line to the line ready for the last line? Yeah, going from there.
Well, since these are all integers, okay, so this is multiplication, right?
Right.
This is multiplication, and these are addition. Remember, multiplication and addition are closed. So it just means that when you add and multiply integers together, you get a new integer. Now we don't know what that integer is, so we just call it n.
Okay.
And we're just defining n to be an integer, okay? So
Okay,
it's just
I see.
some arbitrary value that we don't know what it is, okay? But it exists, okay, under closure.
What's the thing you wrote at the end, middle, GCF?
Oh, GCF. Yes, sir. Greatest common factor. Sorry about that. Okay.
Then why would you even need to factor out the 2 to get from?
Well, remember the definition of odd is twice an integer plus 1. Okay, so just to write it in the form of 2n plus 1 or 2k plus 1. Okay, and I know that you guys probably know that 3y plus 4x plus 3 is going to be an integer, but we want to show everybody that it is no matter what. Okay, does that make sense? Okay, good question. Thank you. Okay, other questions? Flush it. All right, other questions, guys? Okay, so we know how to do the algebra stuff, okay, and we understand our definitions, okay, so now comes the fun part, okay? Now we actually have to prove some stuff, okay? Some of these are going to be fairly easy, some of them are going to be more difficult. And what I want to do is I want to show you guys the process for a direct proof, okay? There's going to be some things that are consistent no matter what direct proof we're doing, and then the middle parts are going to change a little bit because that's the algebra stuff. Okay, so here's the 3 steps that I think of. Okay? First, you have to define your variables. Okay? Sometimes there's going to be 1 variable. Sometimes there could be up to 7 variables. Okay? Okay, just like a computer program, you define your variables. Okay? Then you're going to use algebraic manipulatives and your definitions to try to verify or try to prove the statement. And then when I say close it out, what we always say is by definition of whatever we've just shown that the proof is true. Okay, so the first part and the third parts are usually the parts that stay static. It's going to be that middle part that's going to change because that's the algebra parts. Okay, so let's go ahead and try to prove something that we probably think is already going to be true no matter what. We just have to show it. Okay, so I want to prove the following statement using a direct proof. Okay, so for all x, y, z odd, x, y, z odd. Okay, basically, guys, what am I asking you guys to prove with this? Somebody put it in just regular old English
For
language.
all x, there exists y. For all x integers, there exists a y integer odd such that the multiplication is an element is an odd.
And in fact, it doesn't mean there exists. It just says any two odd numbers, when you multiply them, it's odd. Okay, that's what it's saying. Okay, and it's not just one specific. Okay, it just means if you multiply any two odds, you get an odd. Okay, guys, somebody throw out two odd integers, please. 3 and 7. 3 and 7 is 21, which is odd. Okay, 13 times 13, 169 is odd. 15 times 5, 75, which is odd. Looks like it's going to work, right, guys? I'm just throwing numbers out there. I'm multiplying. It looks like we get an odd. Okay. Now, what if you find a counterexample? What does that mean? It refutes and you're done. You're absolutely right. So, it might be good before you go through and prove it to make sure it's actually true. I mean, you don't want to sit there and waste 10 minutes doing a direct proof when it's not even true. Okay. Fortunately, or maybe unfortunately for you guys, I'm always going to give you guys ones that are true. Okay, unless I make up boo-boo. Go ahead.
Does that actually state that x has to be all odd?
It says for any x and y. So yeah, for any x variable or for any y.
For any x and y.
Correct. So for any x and y in the odd integers, right? So the x is part of that, is an element of. Okay. Oh, that was your question, right? Just the syntax stuff. Okay. Yeah, that's a good question. All right. So let's prove this. Okay. First thing I need to do is I need to define some variables. Okay. Guys, how many variables do you think we need?
2.
2, an x and a y. Okay. So let's start like this. Okay. So I'm going to say for part 1. Okay, so this is part 1. I'm going to let x and y be elements of z odd. Okay, so I'm defining them. Okay, so if you don't do that, if you don't say let them be parts of the, if you don't say that, then unfortunately, technically the whole thing's wrong. Okay, so you have to define that. And I'm going to put this in brackets. Okay, such that x and y are arbitrary but particular. Now, anything I put in brackets in this class is going to be optional, okay? At least for my class, okay? There might be a teacher, okay, for those of you guys that are going to go into computer programming and you have to do like algorithm analysis, or you have to prove something in O notation, all right? If you didn't write that, your teacher might mark the whole thing wrong. Okay, so I just want to write that in brackets saying that in another class you might have to do that. In my class, I'm okay without it. Okay, it doesn't hurt my feelings.
So what do you mean by such that x and y were arbitrary? I know what arbitrary means, but particular. What
arbitrary means that it could be any odd integers, but it has to be specifically one integer.
Okay.
Okay, so it can't assume more than one variable or more than one value at a time. In other words, it can't be a string or a list or a vector of those. Okay, so go ahead.
Is there a symbol that we can just condense that whole thing into? Okay.
Sorry, you've asked a question that I've heard for 13 years of teaching this course. Unfortunately not, sorry. So just write it out. I'll tell you what, if you break your arm doing it, I will give you an A in the course. Okay? Alright. Alright, is that okay so far, guys? Alright. No, don't do it, by the way. Don't break your hand on purpose. I don't need that. Alright. Now, because x and y are odd, don't we know that there's a definition of odd? So, my definition of odd what do we know about x and what can we say about y? So, if x is odd, what does that mean that x has to be equal to?
2n plus 1.
2n plus 1, right guys? Nice. So by the very definition of odd, x is equal to 2n plus 1, or n is in what domain? Integers, right? If we don't say it's an integer, that means n could be a vector space, n could be dodecahedron, it could be whatever it wants, okay? But now that we define it as an integer, it has to be much better behaved. Now, what do we know about y? What's the definition of odd for y?
Same thing, 2m.
Not the exact same thing, but
At 2m,
2m plus 1. Because what if that mean, what if we use the same variable? Doesn't that imply that x and y have to be the exact same? Okay, and we don't want to imply that. So we could use 2m plus 1, we could use 2k plus 1, 2 theta, 2 beta, 2 zeta, whatever you want. Okay? I'll just use m and n.
Would the M pretty much cover the particular part of
Yeah.
the bracket?
Yep, that's exactly right. So this is an arbitrary but particular, and this is an arbitrary but particular. Okay? We don't have to write arbitrary but particular every time because it's covered in the x and y definition.
So if they were both N, then they both, one of them would be particular? Or would they
Well,
still
actually, if they were both n, that means they're both the same integers. And we're only proving that if you multiply the same odd integer together, that's going to be odd. We want to prove it for any odd integers. Okay? Okay.
Just quickly, can it be both an even and odd integer?
No.
Well, because I see it says n is an integer, but does it have to be, it can be odd or even?
M and N can be.
Oh,
but
M and
you
N
have
can
to
be.
add the 1. And it
But
makes
then you add the 1 and it makes it. So like let's say n was 3. 2 times 3 plus 1 is 7.
Yeah.
Let's say n was 4. 2 times 4 is 8. 8 plus 1 is 9.
Right,
This
okay.
is the very
Yeah.
definition of odd. So it doesn't matter.
I'm just piecing through.
No, that's okay. You're allowed to piece things together. Okay. Guys, that's part 1 of the proof. Okay. If you do that on the exam, it's worth 10 points. That's 3 out of the 10 points. Okay. Now this is where we're going to get the majority of our points. Okay. We're going to use algebraic manipulatives and definitions to prove the statement. Okay. So this is part 2, if you will. Okay. What I need to do is I need to substitute back into x, y. Okay. So by substitution, xy is equal to what? What can we say about xy? Not yet. I mean, that is true.
2m plus 1 times 2m plus
Right. Because remember, if you just say it's going to be an integer, we don't know if it's odd or even, right? And don't we want to prove that it's going to be an odd integer? Okay, so we're going to substitute the very definitions that we just implemented. Good done. So 2n plus 1 times 2m plus 1. Okay. Everybody can see that, right, guys? We just defined x and y to be 2n and 2m plus 1, respectively. Okay. Now, this is what we just did. We had to show that this is going to be an odd integer. Okay. So, how do you guys think we might go about trying to show that this might be an odd integer?
foil it.
Yeah, FOIL it out. We don't like foiling, we like factoring better, but this is a case where we have to FOIL it. So, let's multiply this out. By multiplication, 2n times 2n is 4mn. 2n plus 1 is 2n. 2m times 1 is 2m. And then 1 times 1 is usually 1. We can say that that's true by multiplication, right guys? We just did the polynomial multiplication. So we can say this is by, now not by closure, but just by multiplication. So, does that make sense to everybody, guys? Just like Algebra 1 stuff, not a big deal. Okay. Now we need to show that this is odd. Suggestions, right?
Factor out the 2.
Yeah, isn't there a 2 in those first 3 terms? It actually looks very similar to a problem that we did earlier today. So I like that suggestion. Let's factor out a greatest common factor of 2. If we factor out a 2 from just the first 3 terms, can't do it from the last term because it doesn't contain a 2, that would be 2mn plus n plus m plus 1. Quantity. We're going to close the quantity there. That's just a regular old GCF. Okay, nobody doubts that. I'll try to make GCF look like GCF this time. Okay. And guys, what do we know about all that garbage in parentheses?
That becomes n.
It's an integer, right guys? Now we have to be careful. We can't call it n, can we?
No,
we
k.
have to call it something different, like k or w or zeta or theta. or a gamma, or whatever you want. But by closure, this is going to be equal to, I just like k, so we'll use 2k plus 1, where k is an integer. Okay. And that's by closure. All right. Now, check out what we've done thus far, guys. Okay. We've done step 1 where we defined the variables. Okay, we just used the very definitions and we implemented those definitions. Then we went through and we just did the algebra. Okay, whenever you guys do these types of problems, substitution is almost always the first step of the algebra part. You're basically plugging back into what you're trying to prove, and then from there you just go through and do your algebra until you get to the form of even, until you get to the form of odd. Okay, does that make sense, guys? Any questions? Go ahead.
But the closure would just be your step 3.
Yeah.
Closing out the 3.
Step 4 technically, because it's 1, 2,
Well, I mean,
3, 4.
just general steps.
Oh, no. Okay, I'll show you the last part. So this is the last part right here. Okay, so I see what you're saying. Sorry about that, Greg. Okay, everybody good with that so far though, guys? Okay, last part is, guys, isn't this the very definition of odd right here?
Yes.
So xy is equal to 2k plus 1, and it is odd by the very definition of odd. Okay, so we could say, thus by above, not def from above, but thus by above, xy is equal to 2k plus 1 and is odd by the definition of odd. And is odd by definition of odd. That just ran out. Okay. All right. So, now unfortunately that's a lot tougher than finding out the output from a circuit, right guys? It takes a lot more time. And that's why traditionally students don't do as well in this section, just because it takes a lot more time to do than some of the initial problems. Okay? Alright, so when I ask you guys to do a direct proof, okay, this is what I'm looking for. I'm looking for these 3 steps, justification for all the steps as well. Okay? And then just some sort of statement that says, oh okay, I can look and I can close that out and just saying that I've used the very definitions to prove this. Okay? So, does this make sense, guys? Any questions about what a direct proof is? Now, I know most of you guys haven't done a direct proof before, so it might look like it's a little confusing initially, okay? Guys, we're going to be doing this over and over and over again, whether you like it or not. Okay, so this is what it is. Okay, so questions. All right, so of course the best thing to do in math is once you do one, you just beat it up over and over and over again. Okay, so let's beat up a few more of these. Okay. All right. So another question, or another problem that we have here. Okay. For all x in z even, x to the 4th is even. Okay. So basically what I'm saying is, if you give me an even number and I raise it to the 4th power, I get an even number out of that, right, guys? Like for instance, and don't write this down, but 2 to the 4th, 16 is even, right, guys? 4 to the 4th is 256. Which is even as well. Even 0 to the 4th, which is 0, is even as well. Okay? And then I'm not going to do 6 to the 4th because I just don't know what it is.
I got a question.
Yes, sir.
If 0 to the 4th is even,
Yeah.
then is 0 to the 3rd is odd?
0 to the 3rd is still even. Okay?
How?
Well, 0 cubed is 0, which is 2 times 0. The definition of even, right? Now, just because this number's odd, that doesn't mean the output's odd. Like for example, let's say I did 4 to the 3rd. 4 to the 3rd is 64, right? So if I raise an even number to an odd power, it's still even. Okay? I'm just proving it for the 4th power. That's all I'm proving it for. Not for every even or odd power. So I don't want you to be confused with what we're actually trying to prove.
I was thinking of the homework, because the homework 0 was considered to be even?
Oh yeah, 0 is an even number. Because it's equal to 2 times 0, which is by definition even.
So it's 1 times 0.
Well, 1 times
That's
0.
not the definition of even.
1 is equal to 0 times 1 plus 1, which means it's odd. Oh, snap.
So we made some mistake on the
So wait.
homework.
Plus 1.
Okay, even numbers, ready? -4, -2, 0, 2, 4, right? And it goes on forever. Okay, those are even numbers, right? Like you guys learned that way back in like 2nd or 3rd grade. okay? Or hopefully you did. I don't know what they teach in Common Core anymore. -3, -1, 1, 3, 5, those are all odd numbers, right guys? So that's the definitions of even and odd, and you can make it fit these, okay? So does that help out any, or hopefully not racing like, 20-some years of learned math? Oops, although that might not be a bad thing. Okay, so regardless, let's go back here, okay? So for all even integers, x to the 4th is in z, okay? It looks like it's true, right? We didn't find a counterexample, so let's start out by defining the x variable, okay? So this is, if I was to do this in steps, let's let x be an element of z even, okay? And in brackets, again, you don't have to put this, but x is arbitrary but particular. Okay. What's the only possible thing that we can do at this point with x? Yep, we can say x is equal to 2n for some integer n, right? That's all we can do because we've just defined x to be even. Okay? So, by definition of even, x is going to be equal to 2n, and I need one more thing there before we can conclude part 1.
N is an element of z.
That's correct. Nice. Okay, so n is an element of the integers. Okay. Let's say you're on an exam and you forget that. That's a half point. Okay. On the homework, I might just write it in there the first time. Okay, but if you keep doing it over and over and over again, then I'll take off points because I don't like writing in right answers. Okay. All right. So that's part 1, right? We can all do that. Okay. Part 2. We need to start with what, guys? Rhymes with substitution. Substitution. Good. So, by substitution, see, sometimes you just need to write here. So, by substitution, okay, what are we substituting back into, guys?
2n into x.
Not just x, but
X to the 4th.
x to the 4th power, right, guys? Because we already know what x
2n
is,
to
right?
x, and x is 2.
Okay, so we're going to say x to the 4th is equal to quantity 2n to the 4th. Okay, so we are substituting into x, and we're substituting into the statement x to the 4th power. Okay, so, and that's because that's what we're trying to operate on, right, guys? Okay, so that makes sense so far? All right. We need to show that this is even. Okay, suggestion as to what you guys might think to do next.
Expand?
Expand it. So instead of 2 to n to the 4th, what would you write that as?
16 to the n to the power 4th.
16 n to the 4th. And that's just by multiplication. Technically, it's the product of a power rule, but nobody cares what those rules are called, except for people that teach algebra. So this is just going to be by multiplication. How do I know, or what can I do to show that 16n to the 4th is even?
So take 2, then 8n to the power 4.
So we're going to factor it, right?
Yep.
16 is factored into 2 times 8, right? Now why not 4 times 4? Why not 32 times a half?
Because you have to know the definition of 2n.
So we need to look for that definition of even. So twice 8n to the 4th. Okay, that's just by factoring, and that's because we want to show that 16n to the 4th is even. To show something's even, it has to have a factor of 2. Nice one. So this is going to be written by factorization, or we can just say factor. It's not a GCF, but you can just write factor. Okay, if you write GCF, I'll just scratch it out and say factor. That doesn't
So what's the difference between GCF and factor?
Greatest common factor means there's 2 terms.
Okay.
This is a singular term with 1 factor, and you're only factoring out that coefficient.
Good.
Okay, does that make sense, Art?
Yeah.
Okay. Again, if you guys wrote it, I'm not that hard up on it. Okay. Guys, what do we know about 8n to the 4th?
That is equals to k.
Something integer, right? K. Okay, so by closure, this is going to be equal to 2k. And k is just not an even, but Just any integer, right? Good. Even though this actually would be an even integer, since it's 8 times a number, okay, but we don't care about that. That's going to be k in z, okay? And guys, isn't it obvious, okay, this is a self-contained proof that no matter what number I plug in for k, we ended up with some sort of even integer, okay? So if I take any even integer, raise it to the 4th, I still get an even, okay? So, for step 3, we're going to say, thus, x to the 4th is equal to 2k and is even by the very definition, or you could just say by definition of. Okay. Step 3 is the easy part. You've gone through, you've done all the hard work, then you just got to tell everybody what it means. Okay. All right. So guys, those are 2 very basic proofs. Okay, on a scale of 1 to 10 in this class, those are going to be about 1.5s. Okay, so they will get more difficult, but I just wanted to start you guys out easy with this stuff. Questions about either proof, guys? Okay, hopefully not too difficult. It's just new. Okay, and just because something's new doesn't mean it's difficult. Okay. So let's go ahead and try to take a look at another example. Okay, now this one says that if I have some even integer, -1 to that even integer is 1, right? And you know this, right? Anytime you raise like -1 to the 16th power, it's positive 1. Now we get to prove that. Okay? So let's go ahead and prove something like that. And again, the first thing that we have to do is we just have to define some variables. Okay? So if I was to define a variable, or variables, let me ask you guys this first. How many variables do we need? 1, because that's all we have in the problem, right? You guys are getting good at this. Okay, so right away, let's let n be an element of z even. Okay, and then in parentheses or brackets, sorry, n is arbitrary but particular. What's the only thing that we can say about n at this point? Or nothing?
It's equal to 2m.
Yeah, we can say it's equal to 2m, 2k, 2p, 2 theta, whatever you want. Nice. Okay. So we're going to say that this is, by definition of even, we can say that n is equal to, you said 2m, correct? Okay, that's fine. Yeah, you never want to use a recursive definition with this. That would be kind of painful. So n is equal to 2m, and obviously m is going to be equal to an integer, or a set of integers. Okay, so that's easy enough, right guys? Alright, so that's step 1. We can all do that. We can define a variable, we can use the definition of that variable. Okay. Now we have to substitute. Okay. Now, all we're trying to do is we're trying to show that -1 to the n is equal to 1. Okay, so here's our substitution. So by substitution, okay, -1 to the n is equal to what, guys? -1 to the 2m. Sounds good. Nice, Mr. Weber. So -1 to the 2n. Okay. That doesn't hurt anybody's feelings. It might hurt your wrist because we have to write a lot, but such is life. Alright. Now, we need a few steps algebraically to show that that's actually equal to +1. Okay? And you guys might not know the names of the steps, but you might know the process, okay? And that's what we're trying to fill in. So, if I was to ask you guys to show that that's equal to +1, somebody give me a suggestion.
Put them all on the same side and then factor.
Well, let's just focus on this right-hand side. But I like what you said about factoring. So, Don, did you have an idea? Oh, I see what you mean. You meant subtract this and then factor out like a -1 or something like that. Not a bad idea, okay? It won't help us in this instance, okay? But I like the idea of you seeing that common factor. So Did you have another suggestion, Don, or was that's okay, that's better than what I had. So I'm just hoping you guys know what you're doing, because I have no idea. So, another suggestion maybe, guys? So, Paul.
You can do like -1 to the 2 times.
So, and Paul, would you mind terribly, I like your idea, I'm going to steal a little bit more out of that. I'm going to write it like this, because I'm just that guy that likes to steal ideas, okay? But I think he's right, in fact I know he's right. Guys, isn't it true that you could factor off that m and just rewrite it like this? This is actually going backwards from something called the power of a product rule. We could just say factoring if you want to, that doesn't bother me, okay? Seems like we use factoring a lot. So remember when you guys were in Algebra 1 and your teacher said, oh yeah, you gotta learn how to factor, and you're like, when are we going to use this shit? And you're like, never. Well, we actually use it now, okay? So this is by factoring. Okay, very nicely done, guys. All right. What's the next thing you guys might do at this point?
Square them.
Yeah, -1 squared is going to be 1, right guys?
Sure.
Last time I checked, that's basic computation. Nice. So by computation, this is equal to 1 to the m. Okay. Nobody doubts that, right guys? Okay. What do we know about 1 to any power?
It's equals to 1.
It always equals 1. It's a multiplicative identity, right guys? So if you want to write multiplicative identity, you can. If you just want to write by computation, that's fine too, okay? So I'm going to be fancy about it, because I got a master's degree. Might as well. Multiplicative, now I can't spell it. Multiplicative identity. And even if I could spell it right, you guys couldn't read my garbage up here, so, which is equal to 1. Okay? You could write computation, calculation, definition of 1 to any power. Okay, there's a lot of ways that you guys could justify this. All right. Guys, aren't we done? Haven't we shown that by the steps above, -1 to the n is equal to 1? Okay, so we've proved that whenever you raise -1 to an even power, it gives you positive. Okay, so we can say by above. Now there's no real definition that we've shown, right? So by above, we could just say -1 to the n is equal to 1 for all n in z even. Go away. See if you talk to it, it makes a difference. It's like when you're in an elevator and you're pushing the button a million times. That never works. Alright. So what we're seeing, guys, is sometimes we have to be a little bit sneaky with our algebra. Okay, for those of us that are suffering through Calc 2, we know that algebra is the bane of our existence, and trigonometry, and partial fraction decomposition, and Calc 2 in general, regardless. Alright, questions I can answer about integer stuff, guys, so far? We haven't looked at perfect squares, so let's take a look at an example of something to where we have a perfect square. Okay, go ahead, Ryan.
Would any of these problems have like existential?
Oh, I can't, if you do existential, you just prove it by existence, okay? So it's really easy to show that. So, and we've already done the easy stuff. Now I'm making you guys suffer. That's okay, it's a valid question, okay? So I'm not going to give those to you guys because they were just too easy, okay? All right, other questions, guys? All right, so let's go ahead and do this one with a perfect square in it, okay? And then I'm going to let you guys practice one just to make sure you guys get an opportunity to work through this. Okay, so for all x in the integers, okay, 5 quantity x squared plus 1 minus 4 quantity x squared plus x minus 1 is a perfect square, all right? Now, this seems really far-fetched, right, guys? So maybe we want to plug in a number to make sure it works. I mean, that couldn't hurt, okay? So let's just plug in a number, see if it works, okay? Let's plug in 0, because 0 is a nice number to try, right? So this would be 5 times 1, which is 5, minus 0 minus 1. 5 minus 0 is 5, minus 1 is 4, which is a perfect square. Okay, so it works for 0. Let's see if it works for 1, just to see if it works. If I plug in a 1, 1 plus 1 is 2 times 5 is 10. 1 plus 1 is going to be 2 times 4, which is 8. 10 minus 8 is 4, is 2. 2 minus 1 is 1. 1 is a perfect square. So just by trying a couple of them, it looks like it works. Okay. Now I'm not saying sit there and try to find a counterexample, because if it doesn't work, you probably try 1 or 2 and it doesn't work. Alright, so we need one variable, right guys? So let's let x be an element of z. Not z even, not z odd, just z. Okay? X is arbitrary or particular. X is arbitrary but particular. Yawn. So really, there's nothing we can do with x, right? I mean, it's just even. It's not odd. It just is what it is. Okay? So literally, guys, this is step 1 right now. Well, that's not exciting. Because we don't have a definition for x, do we have a substitution step? No. So what do we do? Yeah, just go ahead and do the algebra, right? Let's just beat it up. We're going to factor, we're going to FOIL it out, right guys? We're going to expand, okay? So, we're going to say that by multiplication, this becomes 5x squared plus 5 minus 4x squared minus 4x minus 1. Okay? So all we did, guys, was we just did this distributive property. Okay, that's it. Okay? We can all do that. We've done that thousands of times in our lives. Okay? Suggestion at this point.
By computation.
Combine like terms, right? That's usually what we do. Okay, so let's just take a trip back to polynomials 1. We are going to combine like terms. And correct me if I'm wrong, guys, but by like terms, what do we get? I think I forgot an x, didn't I? No, I didn't. We get x squared minus 4x plus 4, correct?
Yes.
Okay.
Can you write like by computations instead of like terms if we don't remember right?
Yeah, it's fine.
That's
I mean, that doesn't hurt my feelings. By addition, if you want to, because that's technically what it is. Okay? After you've probably seen it a few times, you'll be like, oh yeah, it's like terms. Okay. What do we need to show? We need to show this is a perfect square, right? Suggestion?
X plus 2 whole square, right?
Okay. We can factor this, right? So by factorization, and Art, I'm just going to change one thing in there. Doesn't this become x minus 2
Minus, yep.
times x minus 2? Okay, that's just factoring your trinomial. Okay. If you don't trust me, FOIL it out. Okay, I promise it's going to be x minus 2, x minus 2. Which is the same thing as what, guys?
X minus 2 whole
X
square.
minus 2 quantity square. If you want to skip this step and just go right to x minus 2 square because you see the pattern of the trinomial, that's fine with me. If you don't see it, this is what I always teach my lower level algebra students to do. Okay? So once again, by factoring, because that's what we're really doing, this becomes x minus 2 quantity squared. What do we know about x minus 2, guys? It's an integer, right? Let's call it k if you want to. So by closure, this becomes k squared. And of course, k is an integer. So this is probably one of the ones that looks really intimidating, but quite honestly, guys, it's an Algebra 2 problem at most. Okay, that's what we're going to be finding out throughout this class, that most of the operations that we're doing algebraically, no trigonometry, no differential or integral calculus, just straight up Algebra 1 and 2 stuff. Okay? Yeah, that's a good or bad thing, depending on how good or bad you are with algebra. All right. So, isn't it true that by above, can we say that this nasty thing that we started with is equal to k squared? Okay, so by above 5 quantity x squared plus 1 minus 4 quantity x squared plus x minus 1 is equal to k squared. And is that good or bad?
Excellent.
That's very excellent, because what does that mean, guys?
A perfect square.
It's a perfect square by the very definition of perfect squares, right guys? So we can say, which is a perfect square by definition of perfect square.
Would you not have to include for all x existence in the integer?
No, we already did that up here. So we already know that x is an integer by previous definition. Think of that as almost like a global variable, if you would. We've defined it all the way back up top. So, and you guys know global variables are dangerous sometimes, but in this case it's just math, so who cares, right?
Right.
So, which is a perfect square. By definition of perfect square. I'll get out of your way in a second. Okay. Okay. So, questions about any of these proofs that we've done so far? And of course, I'm going to let you guys practice one of these. Okay?
Why do we not have to define it up top again?
Oh, you mean the x or?
Yes.
So once this x is defined, it's already an integer all the way through. Okay. And then we don't have to define. Now, are you asking why we don't have to define x again down here?
Well, for the last one we did, we said by definition of even, so.
Right. So, but remember, x is just an integer. It's not even nor odd. So we don't have to reuse the definition of even nor odd because we never utilized it.
Alright.
The only definition that we utilized was perfect square, and that was at the end of the problem. Okay, does that make sense, Adam?
Yeah.
Okay, other questions, guys? Okay, let me start you out with this one, okay, because I want to make sure that you guys get a good shot at being able to prove this, okay? So, if A and B are, I'm sorry, for all integers A and B. Oh, John, you need me to go back up?
Yes.
Okay, that's all right. Is that good enough, sir?
Yes.
Okay. All right, I'll start down here. Okay. For any integers A and B, if A and B are perfect squares, then this ugly structure right here is a perfect square. Okay? Now it is true. If you don't trust me, pick two perfect squares, throw it in there, you'll see it works. Okay? So, let's start this out. Okay? How many variables do we need?
Two.
Two. Okay? So, let's let A and B be elements of the integers. A and B, arbitrary or particular. That's funny, A and B, and then it looks like A and B right here. That's not really that funny, sorry. Arbitrary or particular. But there's one other thing that we have to say about A and B in this problem. We have to say that they're both perfect squares, right? Because isn't this a conditional statement? We're saying that if A and B are perfect squares, which means we have to make that assumption, okay? Because this only works for perfect squares. The previous problem worked for any integer x. This one only works for perfect squares. So we're going to say, let's let A and B be integers, where A and B are perfect squares.
You have to write that A and B are equal to like A squared.
Right, we're going to use the definition of perfect squares. Very nice, gentlemen. Okay? So, since we know that they're perfect squares, we have to use the definition of perfect square. Okay? So, what's the oh, go ahead, Brian.
So do we still have to write that A and B are perfect squares in a sentence, or can we just write it?
Yes, we still have to do that because we can't just jump right to the definition of that without defining that. Okay? So we first define it, then we use the definition. Okay? So, by definition of perfect square, so what can we say A is equal to by definition
Square
of
root
perfect
of
square?
A.
What's that?
Square root of A.
Not square root of A. N square, K square, whatever you want to do, okay? So let's say A is equal to N squared, okay? Where N is an integer, right guys? And B is equal to another integer squared. Let's say M squared, K squared, doesn't matter, as long as it's different. Okay, so that's how we're going to start this out. Provided that my in the element is an element, looks like a little bit of an element. Let's try this again. There we go. Okay. Now, what I'd like for you guys to do is to try to finish this off. Okay? So, do your substitution, do your algebra, and see if this works out for the rest of us. Okay? So let me give you guys a good 5-6 minutes. Okay? You guys can work together if you want. If you don't like the person next to you, then, oh well, sorry. Move around. And if you move around to anybody and you still don't like somebody, it's probably you. It's not them. You're just a jerk. And of course, if you need help, raise your hand. Okay, certainly want to help you guys out if I can.
So if we do this, we have this a squared plus twice ab plus b squared, but since there is no twice.
Oh no,
so-
there is 2. There should be. Oh. Yeah, there should be a 2 in there. Okay. I have to write a 2 in there to make this true.
Okay.
Otherwise, it's not true. Sorry, guys. Let me change the problem just so it works. You can't do that on a quiz or exam. Sorry. But there should be a 2 right here. I just made a copy error when I typed it. Sorry. Sorry. My bizzle, my bizzles. Apologies. Just write on the teacher evaluation. It's fine.
Make multiple mistakes.
How do you know somebody else didn't type this up?
You said that right now.
I mean, that's
You said I.
Oh no, I made a mistake. That's fine. I'm just asking him how he knows.
Maybe your mistake was in saying I.
It might have been. Maybe my mistake was turning down that job at APG for 3 times as much as I made here.
Maybe.
Maybe.
Now, should we use like factorization or GCF? Because there are 2 variables over here.
Neither.
Neither.
Just regular factor. Oh, I'm sorry, just factor.
by factor.
Okay, yeah, it's not GCF. Sorry to torture anyone. And by the way, if you can't justify all the steps, that's okay. Okay, we're still learning how to justify the steps. So, but the algebra you guys should be fairly competent with. Oh, right, I'm sorry. Go ahead. Sir.
Why do you have a two as the one?
Well, what happened was, okay, I decided that to make the problem work, I put a 2 up there.
Oh,
Otherwise, it wouldn't work without it.
gotcha.
Yeah. Now, and I did tell the class that you're not allowed to do that on the examination. Just like change the problem to make it work. So, sorry about that. Being a teacher, I do get some sort of privileges, and that's one of my privileges, that I can change the problem to make it work. Take a couple more minutes, guys. I think there's there's only about maybe 2 or 3 algebra steps. So, Art, did you want me to come back and look?
Yeah, I think I'm done.
I'm a bit of a math pervert. I like to watch. Oh, that's sexy. I like that. Yeah, that's hot.
All right,
You
thank
know
you.
what I like.
Thank you.
Things that you should not say to another man. Take 1 more minute, guys. We'll go through this answer together. And then we shall move on. So, I'm hoping that when you guys started, you performed the substitution, okay, and you plugged into this revised statement up here. Okay, so instead of having a plus 2ab plus b squared under the root ab, n squared plus 2 roots of n squared plus n squared. Okay. Can somebody tell me algebraically what they did next to be able to simplify this, or what they thought they could do with this?
N squared plus 2nm plus m squared.
So we have the product of 2 perfect squares under a radical, right guys? Well, if you're squaring and taking a square root, aren't they inverse operations? Now that's true for multiplication, but not for addition and subtraction. Okay, so if you guys go into your, if you guys go into your Calc 2 class and you do this, square root of x squared plus 1 equals x plus 1, okay? You just violated the trigonometric substitution rule and your teacher might punch you in the face. All right, hopefully they don't. I don't know.
Is that secant or tan?
What's that?
X squared
That's
plus
tangent.
tangent.
Yeah, that would be 1 tangent of theta. Okay, so we're going to say n squared plus 2nm plus m squared, okay? That's just going through and using a square root on those, okay? You could just say exponent rules or radical rules. It technically is a radical rule, okay? So, radical or root rule, okay, that works. Okay. So, what's the next thing you guys might have done at this point now that you have at least no more radicals in this problem?
Factoring.
You can factor it, right guys? Isn't that like the form of a perfect square binomial? Okay? So this would factor, if I was to factor that guys, what 2 binomials would that factor into?
N plus m times n plus m.
Yep, n times n plus n times n,
N
plus n times m. Sorry, I just couldn't alliterate it nicely. Okay, so this is n plus m times n plus m. Okay? Otherwise known as n plus m squared, right guys? N plus m quantities squared. Okay? That's both, and both of those are factorization. And then guys, what do we know about the variables n plus m? What do they simplify into?
K squared.
Yeah, some variable squared, some integer squared, excuse me, okay? We can call it k or p or whatever you want, okay? I'll just say k by closure. K is an integer. So this is by closure. Okay. And I want you guys to notice that nothing up there is above algebra 2. Okay, nothing is too sneaky. The factorization might be a little tricky because, you know, we don't factor trinomials that have 2 variables in them all the time. But hopefully you guys can see how that works. Okay? So guys, isn't it valid to say that by above this is going to be equal to k squared, which is a perfect square by definition of perfect square. I'm going to write it over here, just because I ran out of room. Okay, so we're going to say, for step 3, if you would, thus, a plus 2 roots of ab plus b is equal to k squared, which is a perfect square by the very definition. We can just say by definition of perfect square. All right, so let me give you guys a moment to copy that down, okay? And then we're going to go ahead and start on rational stuff. Everybody good with this, guys? Any questions I can answer about the process that we're going to utilize to be able to go through and illustrate how this direct proof is going to work just for integers, right? Now we haven't gotten to rationals, radicals, floors, and ceilings and all that yet. Okay, we will. Okay. So guys, let's briefly take a look at the definition of rational numbers and maybe be able to show a few things rational, and then next time we'll probably get to the proofs of this stuff. Okay, so, John?
Oh, yeah, so basically what you're doing, like two things, you're finding the well not just two things, but I mean, you're finding like the definition of something, like an odd number, or just whatever it says, odd, even, or a perfect square, maybe that, and then you just plug that equation into the equation that's in the problem.
And then you just do your algebra from there. I think you said it pretty nicely.
Yeah.
Okay? So you use your definitions, even, odd, perfect square, whatever it might be. Then you plug it into the original problem, and then from there it's just algebra stuff. Okay? Good way to think about it. Okay. Other questions, guys? All right. So, a rational number. Okay. If a and b are integers, a rational number is the quotient of two integers. Okay? So r can be written as a over b, and a and b share no common factors. Okay? So basically that just means it's in lowest terms. Okay? I can show that 37 very easily is rational, right? So how can I write 37 as a rational number?
37 over 1.
37 over 1. In fact, couldn't I just put any integer over 1 and show it's rational? Okay? So 37 is 37 over 1, which means that it's rational. Okay? Easy enough, right guys? We wish the entire exam was that question. Okay? 0.83 repeating is rational. We just have to show it's rational. Okay? And maybe some of you guys have seen the trick with being able to show that a repeating number is rational without using a geometric series. Okay? I know some of us could do it with a geometric series, but not all of us have suffered through Calc 2 yet. Okay? So did anybody remember, or has anybody seen the trick where you can show that a rational number that a repeating decimal is rational? That's okay. What I'm going to do is, this is for part 2 of this. Okay? So let's let x be equal to 0.83, 83, 83, 83 repeating. And because there's two values, or two decimal places that keep repeating, what I'm going to do is multiply it by 100, okay? Because that would move the decimal point 2 places to the right. So, this implies that 100x, and again, because only 2 digits are repeating, I would say 100. If it was 3 digits, it would be 1,000. If it was 4 digits, it would be 10,000. Okay? Guys, isn't it true that 100x is equal to 83.838383 forever? So nobody doubts that, right guys? I mean, if I just define those as variables or even strings. What if I subtracted those? What if I took 100x minus x? Now, clearly, 100x minus a single x is just 99x. Okay, nobody doubts that. We already defined 100x, we already defined singular x. So 100x is 83.838383 . and then minus 0.838383. That's a fancy term in math. It's actually an ellipsis, sorry. But, all right, how does that help us, guys?
Well, that's cheating.
It's cheating? How come?
No, I'm kidding.
It's not cheating, but it's sneaky, right? It's very sneaky. Okay, so how does that help us, guys? Because when we subtract that, we're left with what? 83, right? Because all those non-terminating decimals, but repeating, cancel out. So I'm left with 99x equals 83. Or in other words, 83 99ths. And guys, isn't that an integer divided by an integer, which is the very definition of rational? Now, what if you don't believe me? What do? Yeah, stick it in the calculator, right? And of course, if you were to stick 83 over 99 in your calculator, it would be 0.8383838383. It's our job just to show it's rational. Okay?
So if we were to use this rule with a difference of 2 repeating numbers, it would always be that number over 99?
Correct. Okay? If it was over 3 numbers, what would it be, guys? Not 1,000. 999. If it was 4 numbers, it would be over 9999. Okay? In fact, by the way, how many of you guys have suffered through Calc 2 and done the geometric series of this? Okay. Now you might not remember how to do it, right? But you remember doing it. And that's okay. I'm not asking you guys to do it.
Geometry series were like 1 over x to the power p, right?
Yeah. Yeah, that's how you would do it. And that's a geometric series, okay? So long as x is convergent to that series. All right. Questions I can answer, guys. Everyone feel okay about this much? Okay. My suggestion would be, guys, go home and try to work through maybe the first 5 problems, okay? I think on assignment number 4, so that way you guys can kind of get used to this, and that way when you come in on Wednesday, you're not cold niggles. All right, I do have your guys' examinations, so let me get those back to you guys. All right. Oh yeah, I'm sorry.